All right, so we should be able to see it now. All right, here it is. So when you're doing these on the calculator, this is the 8384, under the stat menu, you have a way of editing your lists. So we want to edit your two lists. We're going to put the data in L1 and L2, then have the calculator do the steps for us. So go back to the toggling through screens here. The X values you see here, 8, 15, 26, 31, 56 are going to go in the L1 column. We'll write these down real fast. And then the other ones are going to go in the Y. Sorry, L2 column, the Y value will go in the L2 column. Okay. Thought I had that all written down, saves a little bit of time. So put the inputs in L1. So the inputs are 8, 15, 26, 31, and 56. Okay, then go over to L2, type in 23, 41, 53, 72, and 103. Now, it's not something you have to do, but if you want to actually see what the scatter plot looks like, the calculator will do that for you. You can draw it by hand, but the calculator, will take less time to do that. You can set your window size so you can see everything. So we're going to go from 0 to 60. And then for the Y values, we'll go from 0 to about 120. And our scale will be 10 on each axis. So if you go to the Y equals screen, there's a second button. You hit second and Y equals, it gets you to the stat menu. And you can plot 3 of these at once. We're going to do the first one here. We'll turn it on. And the only one we're interested in this class is the first one. This is a scatter plot. It'll tell you what list you're using. It'll tell you what your marks are going to look like on the axis. This is usually the one that's easiest to see. And then, of course, this is in color. So my old one is something that's not in color. So if you go back to stat, if you hit edit, you can see your data there. Once the data is in there, once you've turned on the scatter plot, once you set your window size, you can just hit graph, and there it is. So you might want to use this to kind of help you decide, am I even going to use a linear function here? Kind of picture where that line is going to be. It's going to be kind of right about here. The calculator is going to find M and B for us. So you can kind of picture where it is. You don't have to worry about trying to calculate those on your own. Go back to stat, over to calculate, and we are doing number 4. LinReg means linear regression. If you're curious like me, if you've done these problems before, I still haven't gotten a good answer for this. Why is 8 there in addition to 4? What would the difference be between those two? Is there a difference? A and B are just kind of switched. It's like, really? Why would you do it that way? So if you have a good answer for that, let me know, because I don't have an answer for you there. Go to number 4. It'll ask you what your two lists are. So L1 and L2. You can store the equation if you want. We're just going to get the answer. And then go down to calculate. And ta-da, there it is. Here's A. So A is about 1.63 and B is about 13.8. So when you're doing these problems, we're not going to spend a lot of time on accuracy, but there's no reason to write out the whole decimal that you see there. A couple after the decimal point is perfectly fine. So 1.64 should work here. 13.8 should work here for the y value. Sorry, for the b value. So this is interpreted as your slope, and this is interpreted as your y-intercept. So if you were to draw those on the same axis, you can go to y equals screen, type in 1.64 times x plus 13.8. And there it is. So you can see the line is as close as possible to all the data points. Some it goes almost through it, some is a little bit bigger, some a little bit smaller. But it's what we call the line of best fit. If you've done these types of problems before, it's kind of, if you derive the formula, you take these distances you see here, and you try to minimize all those distances. So it's actually a very complicated abstract problem because you can have a lot of data points, and you want to make sure all those distances are calculated, and then putting all that together to get the distances minimized. So if you've had a stats class, you may have seen that calculation before. Not our focus here. We just want to make sure to get that, what we call the line of best fit. So linear regression here. All right, so that one was number, it was number 20. Go back to that page here. Yeah, number 25. So you can write down for number 25. M is equal to 1.64 and B is equal to about 13. And that's all you have to do in section 2.4. If you want to get a scatter plot, go ahead. If you want to practice figuring out your M and your B, take some data sets and go ahead and do that. I think we'll talk about this on Monday. The first two technology projects. One of them has the, trying to remember now, it's from chapter 1, where you're talking about one-to-one functions, compositions of functions, and inverses of functions. The next one talks about linear and quadratic regression. So this would be an example of linear regression. And then the first two sections of the next chapter we're doing will be quadratic regression. We'll definitely be done with that by Monday of next week. So if you want to be looking ahead at those examples. You can go ahead and do 31 there if you want to. If you look at number 31, the data set looks like this. The difference is in number 31, you'll see the X values are much larger than the Y values. So it might be kind of hard unless you do the actual calculations between consecutive values here. I mean, it looks like the Y values are going up by 10, up by 2, up by 2, up by 20. You say that doesn't sound very linear, but look at the X values. These are going up by nearly 1,000, but these are only going up by about 20. So a scatter plot is a much more useful indicator of whether we think the data is actually looking linear or not. All right, so any other questions about that? Anything? All right, I want to do a little introduction to the third chapter. The first two sections are kind of connected. The book is very similar if you've taken college algebra or something similar to college algebra. The first thing you do after linear functions is usually quadratic functions. Our book talks a little bit more about complex numbers before we get into quadratic functions. So let's do a little bit with complex numbers. You really only need them when we're calculating zeros of polynomials. And we're also going to investigate them when we do some trigonometric functions. So I want to do a little review of that because that's the first section in chapter 3. And then we will talk about quadratic functions. All right, so sorry. So make some notes here from section 2. So give you a little brief history lesson here. Back in the day, when numbers were kind of first used, you really only needed numbers that looked like this, which you might refer to as the counting numbers, because you counted things: 1 person, 2 people, 3 people, 4 people, et cetera, et cetera. And we sometimes just call these the counting or the natural numbers. Then there became a need for a way to represent nothing. So 0 is kind of invented. And then this is what we call the set of whole numbers. And another impetus for thinking about why 0 is necessary: if you take a natural number and add it to 0, that number does not change the original number. So we sometimes call this the additive identity. So then there became a need for numbers on the other side of 0. And we of course know those as the negative numbers. But each step along the way here, you can kind of think about, why do you need negative numbers? Well, what could we add to a natural number to produce this new number of 0? There is no number on this list that's going to make this equation true. So we have what are called the integers. So integers are solutions to these types of equations. But you know, on the number line, each of these marks represents an integer value. What's between the integers? Quotients of integers. Those are better known as rational numbers. And one way to think about that is 7 plus 0 is equal to 7. 7 plus x is equal to 0. What number will we multiply by 7 to produce an answer like 1? Not a number we see on this list right here. It's quotients of integers. So these are known as the rational numbers. And you think that's got to fill in all these gaps here, right? Not quite. How do you solve an equation that looks like this? Is this solution going to be a set in the set of rational numbers? No, square root of 7, negative square root of 7 are not in the set of rational numbers. They are not quotients of integers. So this is a set of irrational numbers. Now, the good news is that fills in all the gaps. So everything between these two numbers here is either going to be a rational number or an irrational number. So you figure, well, we must be in good shape here. We got all the numbers. That's a set of real numbers. So the real number system essentially consists of rational numbers and irrational numbers. But you know what? This looks good. What happens if you try to solve an equation that looks like this? So set x squared equal to a number that's not a natural number, but an integer. So for example, like negative 7. Is any number in this system going to solve this equation? It is not. So another number had to be invented. I mean, you think about all these other numbers, they were originally invented, and then there became uses for them in terms of applications. So in this particular case, we also have to invent a new number. If you know what the answer is to this problem, that new number we invent is I. I is the imaginary unit. It is by definition, that's key here. It's by definition the number that is equal to the square root of -1. No real number has this property. It's only this imaginary unit. You could also remember it as I squared is equal to -1. So either way you want to remember it. So I is what we call the imaginary unit. This is the impetus for thinking of a larger number system than just the real number system. So if this is the real number system right here, there is a larger set. It's almost like our universe is part of a much larger system, which we really don't understand, but we know we're not just here by ourselves. There's much more out there. So if we are here in the real numbers, this is a set of what we call complex numbers. So a complex number consists of two parts. It's got a real part, and it has an imaginary part. So this is a real number. This is an imaginary number. So you think about where are you on this picture here? All those numbers listed here, rational and irrational, are in this set right here. If you put them in that set, they are considered to be complex numbers as well. So the real numbers is now going to be a subset of the set of complex numbers. And then there are other numbers that are not part of the set. I, 5i, 4 minus 7 times I. Those are in the set of what we call complex numbers. So there's more than just the numbers we're used to. And one of the reasons for studying these, exactly this application right here. It's not just a square quadratic equations, but higher order polynomial equations. You do not need complex numbers when you're considering linear equations. When you start squaring things, higher powers, this is where we need to at least understand how these numbers, the operations. So that's one of the things we want to focus on, make sure we know how to operate with these numbers. As far as applications are concerned, we don't have a whole lot of applying we can do here. If you want to know what does it look like as a picture, you can graph it, but you need a different set of axes for this. You need a real axis, and then you need an imaginary axis. So you can kind of think of this as an ordered pair. So 4, -7 would be right about down here. If you plot this point, we could think of this as a graph of the complex number 4 minus 7 times I. So if you kind of want to think about it, one reason for doing this, when you're comparing complex numbers, it's a lot harder than comparing real numbers. You say, which number is bigger? Which number is smaller? Does the real part matter more than the imaginary part? You can kind of think of it maybe in terms of distances from the origin. So it's kind of a combination of your A and your B, but there's really no way of describing the order for these numbers. They just exist. They're solutions to certain types of equations. We can write them real parts, imaginary parts. We're not going to be considering any of that. We want to make sure that we can do the operations with the complex numbers. So here are the operations you want to be able to do. Can you write a square root of a negative number using the imaginary unit? Can you take an expression like this and simplify it? Because this is what you get maybe when you solve a quadratic equation. Can you take two numbers that are complex numbers and add them together? Can you subtract them? Can you multiply them? Can you divide them? So we need to make sure we can do all those operations. And also, can we take I to a certain power? We take I to the power of 8, for example. So we want to make sure we can do all of these calculations right here. Now, fortunately, a lot of these are very straightforward. So for example, you want to do the square root of 25. Your answer is going to be 5. But what about the square root of negative 25? You could write this as -1 times 25 under the radical. Then you can write it as the square root of -1 times the square root of 25. That number is 5. This, by definition, is I. So it's the imaginary unit multiplied by 5. So you can have fun with complex numbers. 5i. Okay. This is going to be 4 times I. So if you write 4 plus or minus the square root of -16 over 2, this becomes 4i. And then you simplify as you would. Just keep the I as part of your answer. 4 divided by 2 is 2. 4i divided by 2 is going to be 2i. Now you'll notice when I write these, i's look a lot like 1s. So you will see a tail, you will see a dot. So if you have any confusion here when I write something down, if you're not sure it's an I, you could ask about it, but I try to make sure that it looks like an I and not a 1. So tails and dots, those are my I's. Adding and subtracting, defined exactly as you would expect it to be defined. I'm going to add the real parts. I'm going to add the imaginary parts because those are like terms. 3 plus 7 is 10. Negative 2i plus 4i is 2i. And we always try to write our answers in what's called standard form. So real number plus imaginary number. Subtraction would work the same way. Multiplication, you say, well, if I was like a variable, this looks a whole lot like multiplying 2 binomials together. And that's exactly how you do it. Distribute 3 times 7, 3 times 4i, negative 2i times 7, and then negative 2i times 4i. So 4 terms, just like you would when you're multiplying binomials together. But what happens here is this will be a real number. This will be an imaginary number. This will be an imaginary number, so these two could be combined. This will be what kind of number? Real or imaginary? It's going to be negative 8 times I squared, but remember I squared is negative 1. So this is negative 8 times negative 1. So you're going to get 21 minus 2i plus 8. These two are now both real numbers. You can combine. So it becomes 29 minus 2i. So when you're multiplying 2 complex numbers together, you get another complex number. Is it possible to multiply 2 complex numbers together and get something that is a real number? What happens when you multiply these two together? 5 plus I times 5 minus I. First terms, 5 times 5. Outside terms, negative 5i. Inside terms, 5i. Last terms, I times negative I is negative I squared. So from the previous example, real number, imaginary numbers. What happens to the imaginary numbers? They cancel. Negative 5i plus 5i gives them 0. This is negative 1, real number. Now, why is this an important result? How do you divide 2 complex numbers? I usually do this when I do it in class. How do you divide 2 complex numbers? You don't. What you actually do is you rewrite. So if you are given this problem and they ask you to do, what's 2 plus 3i divided by 5 minus I? What you're actually doing is you're rewriting it in this form, a plus b times I. And in order to do that, you need to make the denominator a real number. How do you make the denominator a real number? I can multiply 5 minus I by 5 plus I, and that's going to give me 26. But you must make sure to multiply the numerator by that same number. So take the denominator in the numerator and multiply by 5 plus I. Because you can't just do the denominator, you have to do the numerator as well. So that gives us 26 in the denominator. You have to multiply these two numbers as you would usual binomial. So 10 plus 15i plus 2i plus 3i squared. And then just make sure to write it in this particular form right here. So 10 minus 3 is 7. 15i plus 2i is 17i. And there you have it. So you just divided. But you really didn't divide, you rewrote. So the first three operations I think are pretty straightforward. Adding, subtracting like terms, multiplying like a binomials. Remembering that I squared by definition is -1. Because I squared is not an imaginary number, it is a real number. All right, so what is I to the 8th power? Here's the good news. I to the 8th power could be an imaginary number, it could be a real number, but not just any imaginary number. It's either going to be I or negative I. If it's a real number, it's going to be 1 or -1. There's a pattern. I, by definition, is the square root of -1. I squared, by definition, is -1, real number. I cubed, we can write as I squared times I, which means we take -1 times I. So it's -I. I to the 4th, you can write as I squared times I squared, because your exponent rules are still going to work. But that gives you what? -1 times -1, which is 1. So there it is. 1, 2, 3, 4 answers. That's all you can get. The pattern then continues. I to the 5th is I to the 4th times I. I to the 6th is I to the 4th times I squared. So these two are the same. I to the 7th is the same as I cubed. I to the 8th is the same as I to the 4th. And it just keeps repeating. Every group of 4 goes from I to -1 to -I to 1. So what happens if you don't want to count like that and you want to find I to the 103rd power? Your calculator can give you an answer, but let's think about our powers here. How can you rewrite 103 so we can find out if the answer is going to be 1, -1, I, or -I? There are a couple different strategies that you can employ. You could divide 103 by 2. You could divide it by 4. How many times does 4 go into 103? A lot of students use 4 because there's no confusion here. I to the 4th is 1. I squared is -1, so you have to make sure if you take -1 to a positive power or a negative power. So 103 divided by 4 is 25 3/4, which means I to the 4th is to the 25th power with 3 left over. By writing it this way, we know guaranteed that this number right here is 1, because it's I to the 4th. 1 to any power is going to give you 1. And then it's just a matter of identifying which answer on the list is going to give us what we want. So in this case, it's going to be -I. So many different ways you can do that. You kind of lose out on understanding how these powers of I work if you just type it into the calculator, because your calculator can do these complex numbers. But working with these powers, 25 times 4 plus 3 gives you the power you're looking for. The other type of problem you want to be able to do, and we don't do a whole lot of these because we usually work with functions of real numbers, but if you wanted to put a complex number in for I here, just make sure you can simplify it. So if we want to do I plus 1 as your input, make sure you can simplify that expression right there. So I plus 1 to the 2nd power plus 4. So I'll multiply these two out right here. I squared. I. 1 times 1 is 1. I squared by definition is -1. These two are like terms. 4 plus 1 is 5. And then your final answer in standard form is 4 plus 2i. So there are a few problems like this in the text, but like I said, when we graph our functions, we're not using complex numbers. We're only using real axis x, real axis y. Solutions to polynomial equations may be expressed as complex numbers in some cases. That's kind of what you want to focus on for the section. All right, so I think I wrote everything down that I wanted to. Okay. So any other questions about that? Haley has a quick question here about today's homework. We do have a couple of minutes here to finish this up. 26 and 28 from section 1.7, and then 38 and 40. It says to use a table, not a graph. Let me take a look at those real fast here. So section 1.7. Okay, so 26 and 28 would be these problems right here. If you're given the graph of this function, you want to make sure you're following inputs and outputs. So 0 is an input. F of 0 should be that output right there. When you're doing f of x is equal to 0, you want to use 0 as the output. So find 0 on the y-axis and get the corresponding x value. When you're doing the inverse, remember your inputs and outputs get switched. So this right here is the input or output for f. It is the input. So we want to take 0 as the input. So that number right there will be your output. When you're solving this equation right here, you want 0 to be the answer, which means this is going to be the input for the function f, where x is the output. So when you're switching the roles of x and y, that's what you're going to get for here and here. 38 and 40. When you're using this table here, same thing is true. 1 is your input. That's going to be the corresponding output. If 3 is the output, you're going to find 3 in this row and find the corresponding input. For 39 and 40, 0 is the input for the inverse function, which means it's the output of f of x. So you're going to be using this number. Solve the inverse of f is equal to 7. Once again, you would find 7 in this list right here and go with the corresponding input. So in some sense, when you're doing inverses, it's easy to set up. You say switch x and y. But when you switch x and y, what else is going to happen? Domains and ranges get switched. Ordered pairs go from xy to yx. Think about what those graphs look like. So when you're using that inverse notation, f inverse of 0 means that 0 is the input for the inverse function, but it's the output of the original function. If you want f inverse of x is equal to 7, 7 is the output for the inverse function, but it's the input for the original function. So if you're given a table of values or you're given a graph, you just have to figure out, am I using x, am I using y? All right, so any other questions? Anything else? So for today's homework, since we are not in class, I would like you to upload it to my Open Math. If you did not do that the first time, let me know if you have any questions about that. If you have more than one page, I showed you in class, I think I did. The combinedpdf.com is a good site to use to combine your PDFs into a single file. And then 10 megs is the maximum you can upload to Math. It'll tell you whether it'll work or not. So there's no need to save it with your high quality methods there, just something that I can read. So, and then I will get those, hopefully get those back to you on Monday. We'll talk about things in class. Chapter 3 is going to talk about higher order polynomial functions. So quadratic, cubic, fourth degree, and then kind of looking at all those together and talking about solutions to equations, fourth degree equations, fifth degree equations. We're going to take a look at graphs. We're going to take a look at doing things algebraically, take a look at inequalities, things like that. Did I really say that to you? I'm trying to remember. I may have said that because we weren't going to be here Friday. If you want to turn it in person on Monday, that would be okay. So upload it or turn it in person on Monday. All right, sorry, we are over. Any other questions? Anything else? I will get this uploaded to our Math site so you can refer back to it. I will post those notes from section 3.1 as well. And then we will pick up in section 3.2 on Monday.